Hello, everyone. Welcome to lecture 7 on finite element method. In this lecture, after a short summary, we want to talk about assembling one-dimensional elements, which are truss elements, in two-dimensional structures. For instance, we want to look into a typical truss structure like this. Let's say you have a truss structure like that. Maybe it is fixed here, maybe fixed also here, and then I don't know, on a roller here. You may apply a force here or a force there. And we want to solve this system. This is what we want to do today. So we learned how to handle, let's say, one-dimensional structures or members like springs, which it could be also similar to trusses. And we mentioned that each spring has a system which looks like that. And then after that, we learned how to assemble several springs using the so-called assembly process, and then by defining the global node numberings. Okay, so these are the global node numbers, and then you can add them together and you assemble your system. The assembled system, it has a size of node, let's say number of nodes times number of nodes. And if you have a problem dimension, this would be problem dimension times number of nodes times number of nodes. So if problem dimension is 1, so if it's a one-dimensional system, this PD doesn't work, doesn't add really to the problem. But if it is higher dimension, the system gets larger and larger. And then this is what we would get. We will get a stiffness matrix for the entire system. But then we learned that usually you have two types of boundary conditions. They are either Dirichlet boundary conditions or Neumann type boundary conditions. So Dirichlet boundary conditions, they may be homogeneous or non-homogeneous, but they are displacement type. And Neumann type boundary conditions, they are force type. If you apply forces, they could be, again, homogeneous or non-homogeneous. Now, if we want to solve that system, the problem with that system is that on some of these points, you apply displacements. On some of them, you apply forces. So basically, the displacements are unknown. And then this is like a unsorted system. This is not nicely sorted, and it's kind of confusing or complex to solve it because these are mixed. So you don't know where are the, let's say, the unknown displacement and where are the known displacement. So the idea of this, what we call static condensation, is to basically sort them and then solve them using the reduced system. So the idea is to split that system to something like this, that all of the nodes for which you don't know the displacement, they come on top. All of the nodes for which you apply the displacements, they come, or prescribe the displacement, they come at the bottom. So the nodes on top, these are degrees of freedom, and then we call these degrees of constraint, basically. Okay, so if you do that, then you end up with a system that, using the static condensation method, you can rearrange the terms, and then you get to this little system, and we call this the reduced system. So this system, if now you look at it, it is basically like AX equals B, and that A is a reduced stiffness matrix. So this is basically the reduced stiffness matrix. And this is, I think, what Batikon asked. Is that true? Is that your question, Batikon?
Yes, hocam. Yes.
Yes. So this is your reduced stiffness. Okay. And yes, we call it here also reduced system. And here you can see I have written also reduced stiffness. So this is what you need to calculate. So basically it tells you that if you have a large system and then many of these nodes are prescribed, maybe you don't have to calculate this case. You can kind of jump over them and This is the part of the system that comes to your solution or the way that you want to solve it. Okay, and then again, we call that whole thing reduced system. And this process of doing something like this, we call it static condensation, or you may think that static condensation, it has two steps. In one step, you calculate the unknown U's, the unknown displacements. In the second step, you can calculate the unknown forces. Okay, so let's say in a two-step process, you can solve your system, and that's that. And then the only question would be, okay, now how would I number the nodes, or how would I distribute these degrees or assign these degrees such that my system will be nicely sorted like that? And in order to do that, I gave you this nice example that you can think of a few people that they are, let's say, left-handed and right-handed, and you want to sort them, so you can assign a degree to them with that little game that we played, and then they can eventually find their placements. So we did that, to play that game for the system that we looked into for several lectures. And then it turned out that it just works, at least for that system, as an example. And then we kind of came to the same process, and then we extended it to a two-dimensional structure. So now we want to look at that system, but to something which has supports that are in 2D. So each point or each node has two coordinate system, X and Y. That means in front of each node number, you don't have just 1 degree, but you have 2 degrees. And then in order to better understand that, we came to this example. So we made the system a little complicated. We assigned these arbitrary node and element numbers, and we talked about the so-called element list, which basically contains your connectivities between the points or between the nodes. And then if you look at that system, we can play the same game that we played previously about this extended node list. So you just write your node numbers, well, the coordinates come here, and then for each coordinate or for each direction, X or Y, you define your boundary condition or the information about boundary condition, whether it is a Neumann type or it's a Dirichlet type. If it is a Dirichlet type, you subtract one. If it is a Neumann type, you add one to the plus number. And then from that, you basically get these numbering, this temporal degree or temporary degrees. Not temporal, temporary degrees. And from that, you can come up with your global degrees for that system. And then also you can imagine that you have also displacement and forces in that system. So if now you count these, it's 1, 2, 3, 4, 5, 6. So it's 6 times 12, basically. Sorry, 6 times 2, that is 12 columns in front of that. So all you have to do next is to assign those numberings to degrees of freedom and assemble your stiffness matrix. And then if you do your stiffness matrix, it's going to look like this one. So you will get 12 by 12 because you had 12 degrees of freedom for the system that we discussed. And then, as I mentioned, again, back to the question that one of you had, there would be this static condensation process basically, and then you come to this reduced system. So you would call this the reduced stiffness matrix. This is the reduced stiffness matrix. All right, so we learned everything and we know how to assemble the nodes and numbers. The only question is how we come from a, let's say, a flat element, a horizontal element, to an element which is an angle theta, let's say, with a horizontal direction, or how we come from a 1D element to a 2D element, or to a 2D space. The element is still 1D. All right, so this is what we want to talk about. And we did that together. The first thing that you can imagine is that if the stiffness of this system is 2 by 2, for this system, we expect to see something which is 4 by 4, because now for each node, you would have 2 directions instead of 1 direction. So your stiffness, instead of 2 by 2, it becomes 4 by 4. And then we went through this proof together in the previous lecture, and we did, let's say, these little mathematical steps, and we showed how we can define a rotation. This is a rotation matrix. How we can define a rotation matrix for the system, for, let's say, for both nodes. It would rotate forces and displacements similarly. And then if you introduce that to your system, you end up with something like this. Now, this would be your stiffness matrix for that system that we talked about. So this would be your rotation matrix. And then if you know what is the stiffness for the flat element, so that is your K0, that is the one which is just, let's say, K minus K minus KK. So that's easy. So if you take that and you multiply it by this rotation matrix and its transpose accordingly, you get this. So for a 2-dimensional system, this would be, or again, for a 1-dimensional truss member in a 2-dimensional space, this would be your stiffness matrix. And then again, all you have to do now is to insert an angle theta for this, and for whatever angle you put in this, you get something you would expect. For instance, if you think theta is 0, so think about this system and you just insert theta equals 0. If theta is 0, all these terms with sinus, they go to 0. And then all the terms with cosine squared, they will be 1. So you see, you get just 1 minus 1 minus 1, 1, which is exactly what you expected from a, let's say, from a horizontal truss element. So what we want to do now is to just look at that again for other angles. And then we want to go to an example together using what we have learned and solve that example that I just drew at the beginning of the lecture. Do you have any questions?
Can I ask?
Sure.
How can we implement these stiffness matrix to the global stiffness matrix? So
We will see it today. It's
okay.
exactly the same process. So we assign those global degrees, like we just talked about it here. So let's say if you have a structure which looks like this, you play that game. So the game that we played here is exactly what we did before. So this should be clear. And then from that, we get these global degrees. And you see these global degrees, these are basically the placements of the nodes in that system. So if somebody has, I don't know, 3, that means that person comes, or that element comes here. So it is, let's say, 3rd row, 3rd column. Okay, so let's say the numbering process is exactly as we did before. And once we have the numbering, we distribute them accordingly. But again, we will do an example. That's what we do actually today. We will do an example today, and then once you implement it in your codes and you watch the videos, I am sure you will see it very, very clearly. Thank you for the question. All right, so let's just think about, I don't know, a few simple examples. Let's say if theta is 0, and I just think of that stiffness, I will put this EA over L outside. if it's a truss structure. So we just saw it that it's going to be something like 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0. Okay, so this is for theta 0, for instance. Now, what if theta is 90 degree? So let's assume theta is 90 degree now. So if theta is 90, let's say if in the previous example, when theta is 0, you are talking about an element that is, let's say, in an xy coordinate system, it's flat. So this would be your element. If theta is 90, in the same coordinate system, this would be this vertical element. So if you think about that, now for theta 0, sorry, for theta 90, all the cosine components, they go to 0. So all these go to 0, these go to 0. And then again, you get this 1, minus 1, minus 1, and 1. So 0, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 0. Okay, which kind of makes sense to you. So again, I want to connect this to what we had previously. You should understand, or you should try to think of these 4 rows and columns as somehow indications of positions of the nodes and their directions. Okay, so if this is, let's say, node 1 and this is node 2, you can kind of imagine why you get those 4 components here, because they connect only the y directions. And you have learned before, if you have a, let's say, a vertical truss, it cannot resist against a horizontal force, for instance. The same thing is here. So if you think about that, it's the same story. So if this is node 1, this is node 2, you can imagine why, let's say, your components, they come here. Okay, so the system, these 2 matrices, or these 2 elements, you know, in their own coordinate system, they would have just a stiffness which would have looked like this. The same holds here. So in a rotated coordinate system, it's always the same 1, minus 1, minus 1, and 1. All right. So that is always the rotated one is always the same thing. It's just that these numbers would be distributed somehow in the bigger system until it gives you a, let's say, similar system or an equivalent system. So now I want to just do the same thing for another interesting angle, and that would be 45 degrees. So let's say you have the same thing. Now you do 45 degrees. Now, if it is 45 degrees, it's getting slightly more interesting because nothing goes to 0 as we expect, or as we expected previously. But then again, I emphasize that if you had a rotated coordinate system, so if this was your coordinate system, let's say this angle is 45 degrees. If this was your coordinate system, that you would have the same stiffness. Okay, it's 1 minus 1 minus 1 1 in that coordinate system. But the thing is that when you want to distribute this now in a coordinate system which looks like that, then you have to use the bigger system that we have up there. Now, you remember that, let's say, for 45-degree, cosine of theta would be the same as sine of theta, and that would be 1 over square root of 2. So basically, in all these components, I mean, except the sine, you get 1 over 2. Okay, so I take that 1 over 2 out for simplicity. So this would be 1 over 2 EA over L. And then basically you would have 1, 1, 1, 1, minus 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 1, 1, 1, 1, 1. Okay, so this would be your stiffness matrix of that element. All right, which again, it kind of makes sense. So you can imagine that basically what we had here is now sort of decomposed into this bigger matrix, or is distributed. And pay attention, you have a factor 1 over 2. Okay, so it's not that this system, because it has more ones, it is more than that. So it's effectively the same stiffness, but it's like that these ones, they are now split into four ones, but then with a factor 1 over 2. Okay, so that's that. Do you have any question? Okay, so I think you understood this. You must know this thing by heart. Basically, you will use it all the time, so you might as well just memorize it. For something like final exam, you will have a cheat sheet, so you can have that too, but I think you will use it so frequently by the time you will just know it by heart. You don't have to worry about that. All right, and now we do an example to understand how to solve a, let's say, a real truss structure problem using what we just learned. And I will use exactly the same sort of drawing that I had at the beginning of the lecture. So let's say it's a line. All right, so this is our truss structure. I draw the nodes with, let's say, with orange to make them clear. So these are the nodes. The orange circles. Then we have the supports. Let's assume there is a fixed support here, or a hinge. Another one here. Okay, there is a hinge there. And then we put a roller here. Then here you apply a force of, on the roller one, you apply a horizontal force. Let's call that force R equals 1. Here you apply a vertical force. Let's call it T equals 2. And then on top, I will apply a force of, let's say, 6, but with angle 30 degrees from the vertical direction. Okay, so this angle would be 30 degrees. So that is F equals 6. So we have three forces, and then we have those supports. All you need are the dimensions and the coordinate system, obviously. So let's say our reference, our origin is here. So this would be our coordinates 0, 0. And for the coordinate system itself, you can just imagine our usual XY coordinate system. Okay, so no particular rotation or anything. Now the dimensions, everything vertical and horizontal is basically 1. So you can imagine this distance here is just 1. And the same holds for these other distances that you see in this picture. So this is also 1. Let me move my coordinate system a little to make space. And this is also 1. All right. So this is the system you have, and we want to solve this system basically. That's what we want to do. So the task is a usual task that you would have for a truss structure, or where you had like ME231, and you would use method of joints, for instance, to solve this. So what you want to do is to calculate the displacements of all the nodes. Now pay attention, I'm just asking you to calculate the displacements of all the nodes. And as I said, this is usually what we also asked you for, let's say for truss structure examples. But I could have also asked you what are the forces here? Okay, so here we know the displacement is 0. I am not asking you to calculate the forces. You could have done that, or I could have asked for it. That's not what I'm asking. I'm just asking you in these points or in these nodes that they have a degree of freedom. At the degree of freedoms, what are the displacements? Okay, again, there are always two questions that can be asked. And for all the structure, you can assume all the E's, elastic modulus of, let's say all these elements are 10 for simplicity. All their areas is 1. Okay. So this holds for all elements, but pay attention again. This is not a must. Sometimes we have different values for different elements. Okay, so we want to solve this together. Is this clear? Good. So the process is exactly as we talked about previously. You should go through your, let's say, typical steps. You need to create your node list and element list. So you first number nodes and elements. Which basically means you create node list and element list. This is the first thing you do. And then based on the boundary conditions or the constraints that you have, you create what we call extended node list. Then you assemble the stiffness But in order to assemble your stiffness, it usually also means that you need to have calculated the stiffnesses of each elements. Okay. So compute elements stiffness or stiffnesses. Yes. All right. And after this, basically after these 4 steps, you can just solve the problem. There is you end up with your reduced system because you have already numbered them correctly, and all you need to do in the last step is to just solve. Okay. These, let's say, these 5 steps are always the same for any, let's say, finite element problem that you want to do. All right, so we are going through these steps together. So since the process is going to be a little long, and I don't want to have a discontinuity in the middle, I suggest we have a short break now, and we can continue after the break, and we will have a slightly longer session to finish this. I want to do it in one, let's say, in one go. And I think you understand the problem. So this is what we want to do after the break. I have 9:07 now. So let's continue at 9:15. So let's have like just an 8-minute break, and we continue at 9:15. Okay, so as we spoke, we want to solve the system. And just before that, and to clean up the picture a little, let's remember from the dimensions, we know that these ones, they have the length 1, and then let's say the diagonal ones, they would have the length square root of 2. Okay, so remember these for what we are going to do next. So now what we want to do is to solve this starting from the first step. The first thing we need to do is to number the nodes and elements. Okay, so let's number them. As I had mentioned before, this numbering by itself is an arbitrary process, so you can do it any way you want. There is no right or wrong here. So I'm going to start, let's say, node numbering from node 1 here on the, let's say, origin itself. Then maybe we just go horizontally. We call this node 2, node 3, node 4, maybe here, node 5. Okay. So we have 5 nodes. Again, 5 nodes for you. It means 10, let's say 5 times problem dimension times n node number of nodes. In this case, it would give you 10. So that large stiffness matrix that we are going to create, it's going to be 10 by 10. So basically, we will have 10 degrees that we need to distribute to these nodes. Those 10 degrees, some of them are degrees of freedom, some of them are degrees of constraint. Maybe you, by just looking at it and by your previous knowledge, you already have a good feeling that you should have, let's say in this case, you have 5 degrees of freedom and 5 degrees of constraints, because you basically can see it, again, visually in this case. All right, so this is that. And then what you need to do next is to number the elements. So let's say this is element. Okay, let me just shift this down for it. let's call this element as element 1. And then again, I draw a square around the element numbers to distinguish them from node numbers. So that's element 1, that's element 2, and also this numbering is arbitrary. Maybe we call this element 3, element 4 here, element, sorry, this would be element 6. It doesn't matter how you number it. I'm just trying to use the same number as I'm using in my notes to make sure we have a consistency between the notes and what I'm writing here. So that's that. So that is what you had to do in your first step. We just, let's say, created these visually. Now you need to obviously write them, and that's what we are going to do in the next slide. So I just copy this. All right, let's say based on the information we have here, now we want to create our node list and element list, and then extended node list ideally after that. All right, so let's keep an eye on this and do our node list and element list. So let's do the node list first. How many nodes do we have? We have 1, 2, 3, 4, 5. So node 1, 2, 3, 4, and 5. And then in front of each node, you should have its coordinates. So I will write it as x, y. And these are the coordinates of that node. So node 1, you can see the coordinates will be 0, 0. Node 2 is 1, 0, 2, 0, 0, 1, and 1, 1 for node 5. Okay, so node 5, you see it's here, 1, 1. And this is the coordinate system that we had, right? XY coordinates. So this is our node list. Nothing super complicated about it. And the next thing you need to do is the element list. Again, we do a similar thing for the element list. Let me just draw the element list on the other side. If you think of the element list, we have 6 elements. So I start one row higher. So elements 1, 2, 3, 4, 5, and 6. And then for each of them, let's say we have node 1 and node 2. Okay, so corners maybe. Let's call them corners. And then again, in one-dimensional element, these corners are very simple because they are basically the ends. But you can imagine if you have a two-dimensional element later, these corners are actually more than 2, and then it would get more interesting. But for here, it's easy. Let's say, I don't know, you have element 1 here. So it goes from node 1 to 5. And that's what you write here. So this is node 1, this is node 5. Then you would have element 2. It goes from 2 to 5. Then you have element 3, which goes from 2 to 3. element 4 goes from 3 to 5. Element 5 goes from 5 to 4, or 4 to 5, depending on how you want to look at it. Let's say 4 to 5, so that we look always from left to right. And element 6 would be between 1 and 2. Okay, so this is the element list, or connectivity again. All right. And then again, the importance of the element list, maybe you cannot exactly appreciate it now when you do these type of problems on papers, but later when you want to actually program it and you want to run let's say, run your code, you usually have this loop over the elements, and elements should know its node. So later you can appreciate why we do this. Let's say when you program it. I mean, visually you already see the connectivities, so it's rather trivial to just observe it. Okay, so I'm going to remove this and create the extended node list. By the way, again, let me just go back to the example. So we just did this. We have numbered the nodes, we have numbered elements, but we created node list and element list. We did that, and now we want to create the extended node list. So this is node list, this is element list. What we want to do next is to extend the node list to get the extended node list. And we do that by the same process that we had learned before when we learned how to number the degrees of freedom and so on. So let's do that. Now in front of each node, remember we said we draw we write their coordinate system, and then after their coordinate system, we would have this so-called boundary condition information. Okay, so now the next two columns, again, it would be somehow X and Y if you want. So this is indication of the coordinate, or indication of the coordinates or directions, but this is like boundary condition info. So for node 1, what are the boundary conditions?
Directly.
Directly, right? So this is for node 1. For node 2?
Neumann directly.
Node 2?
Neumann directly.
Again, node 2? Neumann, right?
Displacement?
No, T is the force, right? So displacement is always like that. And that's a very good point, by the way, thank you. In this course, also, when I want to prescribe a displacement, I usually draw it like this. I mean, for instance, I would write like 1 centimeter on top of it so that it looks different from a force. So these are forces, but you have, let's say yeah, thank you very much. Your question is valid. Yes, the T and F and R here, they are forces, basically, all of them. They are not displacements that we have, okay? Then 3.
Neumann directly.
Neumann directly, right? And node 4. Directly, I suppose, right? It's constrained completely. And node 5, it is completely free. Well, I mean, it has force, but force is also a free. It's a degree of freedom, basically, right? So it's a Neumann. Okay, so this is boundary condition info. And then if you remember, we had this game that we would play next, and we assign these temporary degrees to this. Okay, so we want to do that now. So again, we would have these two columns. And now here I want to prescribe some sort of, let's say, temporary degrees. So we do that counting, as we said. So we start from the first one. So let's say we are at 0, and then you would see your first Dirichlet. You subtract 1, -1. Then the second Dirichlet, so -2. And then you see your first Neumann, 1, and then 2, 3, -3, -4, -5, 4, and 5. Okay. And as I said, when you have programmed this using those two loops that I mentioned previously, this is an automatic process, right? I mean, you don't need to even think about it. Just you go through these things, and because you have DD, you get -1, -2, and then NN 1, 2. So it just adds because it's an N, it adds to the plus. If it is a D, it subtracts from the minus. That is the idea, right? Do you have any question? So this process is exactly identical to what we did. So what is the largest positive number we see here? 5. So degrees of freedom, then it's 5. We have 5 degrees of freedom, which you can actually see from the picture. So you have 2 degrees here, 2 degrees here, and 1 degree here. So you have 5 degrees that they are free, they can move. And you have 5 degrees, so 2 here, 2 here, and 1 here, that they cannot move, they are constrained. So you have 5 degrees of constraints. That's why the largest minus number is -5, and then the largest plus number is 5. So degrees of freedom is 5, degrees of constraint also, let's say 5. This comes from the, let's say, absolute value of -5 if you want. And as I promised previously, if you add them up, they give you 10, which is 2 problem dimension times number of nodes. Okay. Again, this is a coincidence that this is 5 and 5. It could be 2 and 8, or 3 and 7, or anything else, or 4 and 6, or something else. But it's usually how it works. All right, so we have that. Now, the next thing you want to do is to just assign the global degrees, right? And now for that global degrees, that's what I like about this picture now, because you can even clean the picture. You don't need to know what the picture is. And as I said, this is the way your computer understands the system. Your computer just sees a bunch of numbers. It doesn't know the visual feeling that you have about the system. And that's what we want to do. So this is our extended node list. And now we just write the, let's say, the global degrees here. Okay, let's call this global degrees. And as we mentioned, the plus numbers, they remain the way they are. The minus numbers, their absolute value would be added to, let's say, to the largest plus number, which is the degrees of freedom. So you get 6, 7, 8, 9, 10. So these are the way these are the global numberings of the nodes. And after that, you need also the displacement information and force displacement, force information. I will just write it here so you can then have displacement column, let's say in X and Y direction, and you have usually the force column in X and Y direction. So the displacements, I don't know if you can just remember the system. So let's go back and forth between the pictures a little. If you think about node 1, displacements are 0 in both directions. So 0, 0. At node 2, the displacements are unknown basically in both, but the force in the y direction is known. So the force in the y direction is known, and that is -2. It's 2 downwards. So you would have -2, and the force in the x direction is 0, right? So basically, it's just like that. Now your node 3, you have a x direction force, which is 1, and then in the y direction, the displacement is 0. So for node 3, the displacement is 0 here, but the force in the x direction was what? 1. Okay, so you can kind of see what is happening here. So here, the places that I put these question marks, basically, these are the places that you don't know the displacements, but you know the forces instead. Okay, and then those places where you know the displacements, you don't know the forces. Okay, this is kind of how it works, and it makes sense, right? You cannot know both of them at the same time. And then at node 4, again, the displacements are 0. That means both forces are unknown. And at node 5, okay, node 5 is interesting because now we have a force of 6 that is multiplied by cosine 30, and it's vertical, and sine 30 in the -x direction. So this would be something like f times cosine 30 degree and minus f times sine 30 degree. These are the forces, and then again, that means the displacements are unknown. So you can see again, there are 5 question marks in the yellow, which they correspond exactly to those 5 plus numbers that you had here, which are exactly the first 5 components of the global stiffness. So this is your reduced system structure. All right, so remember what we wanted to do. We did the first step, created nodes and element list. Now we also have the extended node list. This is exactly the extended node list.
Can I ask a quick question?
Of course.
At node 2, we said the force at x direction is 0. But how can we know that exactly? We know the y direction force, it's 2 Newton, but
yes,
couldn't it be exist in x direction also for the force?
well, you can, that is, I think you are answering your question. You can say it exists, but it is 0. That's exactly what it is, right? So if there is no force, it is like there is a force of 0.
But for example, I visualize that. For example, node 3 have an x direction force, and it can stretch the node 2 also.
Yes, but these are let's say external loads, right?
Mm-hmm.
The forces inside the elements, these are not there. The forces inside the elements, you cannot see it in the global system. The global system is only externally prescribed global forces, right?
Mm-hmm.
So that's a good question. So the forces here, and the same with displacement, but I think with forces, these are let's say externally prescribed. Does it make sense?
Yeah.
The forces that you put in the force matrix, these are the forces that are externally prescribed. The internal forces, if you wanted them later, you can calculate them using your usual, you know, remember we had this delta PL over EA, which in this case would be like delta U. It would be the stretch of the element, would be the internal force FL over EA of that element. So once you know the displacements of the two ends of that element, you can connect it to the force that is inside that element. But that would be the internal force. Does it make sense?
I get it.
Yeah, which later, by the way, we also calculate these internal forces. In fact, we calculate the internal forces and we divide them by area, and we call them internal stresses, or these are actually stresses. And these stresses, they happen to be those colorful patterns that you see in a finite element course or in finite element mesh, right? So in your project also, you would implement that. So we will ask you to show these, let's say, the displacement of the structure, but also show the stresses in each element. And those stresses, they would be exactly those internal forces divided by the area of each element. Okay, so that's a very valid question, but again, in the extended node list, it's the forces that we prescribe or we insert, these are the externally prescribed forces. Okay. Any other question?
Are we going to use boundary conditions as logicals in the code? For example, when we are writing the matrix displacement and force, are we going to connect them? Then using, so I didn't understand how we are going to use this displacement and forces in the code.
I'm not sure if I understood the question, but let's say at some point you want to solve a system which looks like this, right? It's KU equals F. So this would be all the forces, this would be all the displacement, and this would be your stiffness matrix. Right? Is that the question?
When we are
you use those first informations to assemble stiffness, you know, the degrees. You assemble a stiffness, but then remember, if you assembled it right, some of these displacements here, they are unknowns, and you put all the known ones here, and then you put all the known forces up there and unknown forces up down here. And then you solve this system using that static condensation like we discussed about. Right?
Okay.
Does that make sense?
Yes.
Yeah, exactly. So you basically, and hopefully, I mean, if we have time, we will do it exactly for this system, and you see. All right. So just to have a connection between this system or this what we have here and then what we had at the example itself, I'm going to just redraw the example and write these degrees on top of the example itself, on top of the picture itself, for our own references. So okay, it's getting a little complicated, but I think it's going to be okay. So I do them, let's say, which color we used here. Orange. So in orange color, I'm going to write these global degrees. So see here, we have at node 2, we have the global degrees 1 and 2. You can see it here. Then let's say at node 1, for instance, you have the global degrees 6 and 7. At node 3, we have the global degrees 3 and 8. At node 4, you have the global degrees 9 and 10. And at node 5, you have the global degrees 4 and 5. Okay, so those global degrees are actually here. Okay, so if this example was given to you in an exam, you really don't have to do what we did here to come up with these node numberings. It's somehow obvious. You start numbering them from the, let's say, the free nodes, and then you start 1, 2, and so on. But if it is your computer, you cannot do that. The idea is to do it algorithmic, okay? And that's why we construct it in this node list, this node list. Okay, so anyway, we have now the system. We know the degrees are distributed like this, and if we have the stiffness of each element now, then we can assemble them according to this, okay? So that's what we want to do next. We want to take this system, compute the stiffness for each element, and then assemble them next to or together, okay? So that's what I'm going to do next. I will just take this system, make it small, and then in multiple slides, so let's say in the next 6 slides, we will write the stiffness for the elements 1, 2, 3, 4, 5, 2, 6, based on what we have on the right side, and then we assemble them, let's say in the slide 7. So we start from element 1. And by the way, for all of these, maybe I also put that other stiffness formula here. You know, we need this stiffness formula altogether. That's really all we do. We just take this stiffness box and we put the angles. Let me put this here. Okay. This online teaching is not so bad. I can do these things. Okay, so that's what we want to do. Now we have the stiffness, let's say, formula for any angle theta. All you have to do is to take that for each element and just calculate the elements. Because I want to emphasize on that EAL factor, let me also just split it into 2 parts. So it would be EA over L times that. And then you can see, we assume that E and A for all the elements are identical here. We assume they are all identical, but the lengths are different. Okay, so I'm going to also put that information here on the corner, but the lengths are different. So that EA over L slightly changes from element to element. Okay, having said that, we can finally do that K1, for instance. So I want to do K1. Now, it's a 4x4 matrix. Okay, so let's say that's that 1, 2, 3, 4. Okay. So what is EA over L for that? Length for, so let's do it one by one. E is 10, A is 1, length is square root of 2. Okay, so EA over L would be 10 divided by square root of 2. And then remember, because the angle is 45 degrees, so each of them would give you 1 over 2. I would also take that 1 over 2 out. Okay, so let me just draw this straight. If you do that, then you get something which looks like, I take the EA as just constant because it's the same for all the elements, but here you would have 2 square root of 2. Again, the square root of 2 comes from L, the 2 comes from the cosine squared, or sine squared, or cosine times sine. And then inside the matrix itself, you would have 1, 1, minus 1, minus 1, minus 1, minus 1, 1, 1. And you can see again, these matrices are symmetric, obviously. Okay, so this is element 1, stiffness. And because later we will need the information, I would also like to add those associated degrees to this. So remember, we always said these degrees basically, how can I say, you can think of it as the XY components of nodes. So let's say element 1, remember we said it's between nodes 1 and 5, right? So this is between and I draw the circle 1 and 5. Okay, which you could also see that information, by the way, in your connectivity. So you remember element 1 is between nodes 1 and 5. So what does that mean? That means these degrees that you have here, this is more like this. This is 1 in X direction, 1 in Y direction, 5 in X direction, 5 in Y direction. And the same here, by the way, 1 in X direction, 1 in Y direction, 5 in X direction, 5 in Y direction. So basically, you can interpret these things like that. This, I don't know, this 1 that you see here, it is the stiffness of X direction of node 1 against Y direction of node 1. Okay, so it's the same game that we played before. And now here also, you know that the global degrees, so I'm going to also add the global degrees to this, which we will use for our assembly. So I'm going to just from now on, I don't write the green information, but you get the idea. So let's say the 1x here, the degree, the global degree of 1x is 6. The global degree of 1y is 7. The global degree of 5x is 4. The global degree of 5y is 5. Yes. So that's how we want to play this game. So this is basically, in terms of global degrees, this would be 6, 7, 4, 5, and the same here. So this would be 6, 7, 4, 5. And as I said, for this example, I just wrote that here, but for the next examples, I will skip over this step. So this information is something that we won't write again. But the information that is more important for us for assembly is this 6, 7, 4, 5 here, 6, 7, 4, 5. Okay, so instead of talking about x direction of node, whatever, you can look at it this way. So this 1 is the stiffness component between 6 and 7. And if you have that assembly matrix, remember we said we would have an assembly matrix. We would have an assembled matrix. We would have the stiffness matrix, which is of the size 10 by 10. Okay, so this would be exactly the thing that comes on the 6 column, 7 rows of that big matrix later. Okay, something like that. All right, so again, I know I repeated a lot, but this is the first time. So the connection between these 1x and 6 and 1y 7, 5x, this is straightforward. I think you understand it now, but it's very important that you realize these numbers that we see here, these are exactly the component numbers of the global stiffness matrix. So these are like the coordinates. Those are like tickets that they give to these components to go to the proper places. You know, it's like you go to the, I don't know, to a theater, and then you have a seat number. What is your row? What is your column? This is exactly that. So we know that this -1 here, it must go to the 4th row, 7th column of the global matrix. Okay, so that's exactly how we will continue with this. All right, so that now that we have the first element, I think it's easy, or it's straightforward to just extend the same game to the other elements. Okay, so I'm doing it like this to sort of indicate its algorithmic or its repetitive aspect or repetitive nature. So let's say we want to do element 2 now. So EA is again the same as before. So it's just EA, but the length now is 1. Okay, so what you get here is just EA divided by 1. Now, element 2 is between nodes 2 and 5. And this time I do the degrees first. So the degrees will be 1, 2, 4, 5, right? So it's between node 2 and 5. 1, 2, 4, 5. Okay, so you just continue with the same order. And then here it would be 1, 2, 4, 5. It's that simple. And then inside the stiffness matrix itself, you just construct the components according to this. What is the angle of element 2? It's 90 degrees. So that's a good angle because most of these things will be 0. You get zeros completely here. You get 1, -1, -1, and 1, 0, 0, 0. Right? So that's that. That's element 2. Do you have any question? It's completely clear, right? I mean, it's a very clear repetitive process. And as I said, the reason we can program it and we can tell it or we can teach it to the computer is its repetitive nature. And also remember, this repetitive nature is only repetitive now because we had all these intermediate steps until now. So now we know exactly how to handle that. So what is the next one? 3. Element 3 is also having the length 1, so it's EA over 1. It's between nodes 2 and 3. that means the degrees are 2x, 2y, 3x, 3y. Now 2x, 2y is 1, 2, 3, 8, basically. 2, 1, 2, 3, 8, 1, 2, 3, 8. Okay. And then again, this one, it basically means 2x. This is 2y. This is 3x. This is 3y. These are, and then the 2 and 3, they come from here. Okay, so this is 2. This is 3. Node. So this is node 2, node 3. Node 2, node 3. Okay. So once you do this numbering, which is now very or fairly straightforward, I think you can do that. So the angle now, unlike the previous case, the angle is 0. So that means you get the zeros here. And that would be your stiffness matrix. Okay. And then again, this is the same story like before. So basically, this tells you that the x direction of node 2 has no stiffness on the y direction of node 3. So it's 0. This 0 means the stiffness of node 1, sorry, on the 1 direction, which is node 2 in the x direction, with respect to 8 direction or 8th degree, which is node 3 in the y direction. Okay. Node 3 in the y direction. This is node 1, node 2 in the x direction, which makes sense because, again, if you think of a truss member like this, you remember it's a horizontal truss member could not resist against a vertical force in the other node, basically, right? It has 0 stiffness. All right, so that is node 3, element 3. Do you have any questions? I just need to mention one thing here because I think nobody is asking. So the angle theta that we use, remember, we always assumed that, let's say, if you have a truss like that, the angle theta is this one. Okay. Now you can imagine if instead of saying that this component, so element 3, if instead of saying that it goes from 2 to 3, if I said it goes from 3 to 2, then the angle, instead of 0, it would be 180 degrees. Okay. But it turns out that it doesn't change the result. Okay. So you just pay attention to that, the node numbering is, let's say, is arbitrary as long as you are careful with the way that you assign the, let's say, the angles. So if you say it is from 2 to 3, then you assume theta is 0. If you said it is from 3 to 2, then theta would be 180. Okay. The same thing with 45 degree or minus 135 or something. And it's okay. You should just start from, let's say, a particular direction and then calculate the angle or write the angle with respect to that. So in this case, if I say I go from 2 to 3, then theta is 0. If I say I go from 3 to 2, then theta is 180. Good. All right, so that is element 3. And then the next thing we want to do is element 4. So the length of element 4 is also square root of 2. And then it's also with 45 degrees. So element 4, 2 square root of 2 comes here. Square root of 2 is the length. And again, the 2 is coming from the cosine squared part. And it's between 3 and 5. So theta is 135 degrees. Let's say we count again. We count like that. And if you just do the same thing, now you would get something slightly more interesting. So you get 1 minus 1 minus 1, 1, minus 1, 1, 1 minus 1, minus 1, 1, 1 minus 1, and 1 minus 1, minus 1, 1. Okay, so it's going to look like this. And then again, you just write your global degrees on that. So element, node 3 in X and Y direction, the degrees are 3 and 8. Node 5 in X and Y direction, the degrees are 4 and 5. So what you need to do is 3, 8, 4, 5 here, 3, 8, 4, 5 here. This is for your element 4. Is everything clear to everyone? Please ask if you have any question. So one of you asked, did I say something wrong in the previous exam? Let me see. So I think one of you asked if it is the same as, or isn't it minus 180? Well, I mean, it's the same thing, right? I mean, you could have said this is minus 180, basically. But we always count as a, let's say, a clock. So if we start from 3 to 2, it would be, yeah, 180. All right, so that's element 4. Now what we want to do is to, again, do the same thing for element 5 and 6. And as I mentioned before, this is a very repetitive process, but we do it only once in this lecture. And I want you to understand this because your homework 2 and 3 and your quizzes 2 and 3 will be completely related to this, and also your final exam would be related to that. So element 5 now. Element 5 is now again a horizontal element. It's between nodes 4 and 5, let's say. So the angle is 0, the length is 1. So you get also EA over L, which is EA over 1, like this ones. So this is EA over 1, this is 1. And then the stiffness itself, it's typical horizontal stiffness. And now you just do the same thing about the degrees of freedom. So this is between 4 and 5. So this would be 4x. This is between nodes 4 and 5. So this is 4x, 4y, 5x, 5y. Now 4x is 9, 4y is 10, 5x is 4, 5y is 5. So it's going to be 9, 10, 4, 5. These are the global degrees. All right. And then finally, we do this for element 6. Element 6 is also flat, it's horizontal. So it's exactly the same thing as it was for element 5, but now it's between nodes 1 and 2. And that means it's corresponding to the degrees 6, 7, 1, 2. Sorry, 6, 7, 1, 2. 6, 7, 1, 2. All right. So you have everything you need to have now to assemble your stiffness matrix. And that's what we want to do. So remember, the stiffness matrix is going to be a 10 by 10 matrix. So I'm going to draw that maybe here. Let's say this is your stiffness matrix. All right, so okay, so let's say these are more or less your columns. All right, I think we have enough now. Good. So this is sort of your stiffness matrix. It should have 10 columns, and if I am right, we have 10 columns here, and then it would have also 10 rows basically. Okay, I will add more rows to this later. But imagine this is a 10 by 10 stiffness matrix. Now in that 10 by 10 stiffness matrix, which I'm going to draw a better version next time, or I prepare it before the next time, it's going to be like that. It will have 4 parts, and then you would have degrees 1, 2, 3, 4, 5 here, because these are your free degrees, and then you would have your 6, 7, 8, 9, 10 here, and then again 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10. Okay, and then everything that you have to do at this point is just going back to those stiffness matrices that you had. You pick those components and bring them to this one. So I do one of them for example here, and I don't know, why don't we do this one? So let me just take, for instance, this one. I go shortly over this again at the beginning of the next lecture, but we don't spend too much time on it. So let's say we come to this example. Here it is. Now, you don't need to know this information anymore. And let's say there is a EA multiplied by this, so we just work with the numbers at this point. So you have these numbers, and they have their coordinates. They have their, let's say, again, that example about the movie theater, they know exactly which row and column they need to go to sit at. So this one here, it comes actually at 1, 1. So I'm going to just write it here. It's going to be here. And then the next one is the 0 comes here. So this 0, it goes at column 2, row 1. The -1 goes at column 3, row 1. And then the last one, the 0, you see, it goes at column 8, row 1 all of a sudden. So it comes here. And then you would do the same thing with the other zeros. So they go to the second row and their corresponding columns. And then you go to the third row and you do the same thing. And then you go to the 8th row. So somewhere here, basically, and you play the same game. So a 0 comes here, and then a bunch of zeros come here. Okay. And then again, in these examples, these are zeros, but they could have been just anything. Okay. Does that make sense? So basically what I'm trying to tell you is that what you should see, or how you should be looking at this is, or that's the way I'm looking at it, is always like that. You can think of it like this, that you just duplicate whatever you have here in your in your head, right? And then these components, regardless of their values, these are exactly what you would add to the global stiffness. Okay, so this thing is going to the 1, 1. Let me write it as a 1, 1 of the global matrix. This is 2, 1. Or I can write it as a subscript so that it looks more familiar to you. I like the superscript because we said superscript means global degree, but just think of it component-wise for now. So this is first row, second column, first row, third column, first row, 8th column of the, let's say these are the global matrix. Okay, so whatever component you have there, they have their information, right? So 2, 1, 2, 2, 2, 3, and 2, 8 of global matrix again, and so on. So basically what you need to do is to take this information and just distribute them in the matrix. And it's a very, very, as I mentioned, I mean, in terms of labor work, it's a time-consuming work. Okay, so it's sort of laborious in that sense, but it's a very algorithmic process. So again, if you have done everything correctly, this is just some loop in your computer, and then you know you have a matrix here, it's 10 by 10. You would just say, okay, read this component, look at these associated numbers, and then add it where it should go to the global matrix. Okay, so you just create a matrix which is, we usually say zeros of 10 and 10. So 10 rows and 10 columns, it's all zeros. And then you have a loop over your elements, and then you keep adding these numbers to that matrix. Okay, and once you have that matrix, then you have that system that we talked about previously, or that reduced system. So you would have a stiffness which has these 4 parts, then you have a displacement that it has these 4 parts, and you have a force that it has this. So the force, these 4 parts. So this would be prescribed forces, unknown forces, and then this would be, let's say, I don't know, maybe we call it KUU, and then we call this KUP. Okay, so once you have this, then you can just solve for UU, and that would be it. Okay, this is just it. At that point is only that static condensation, which we did for one-dimensional problem. Okay, so this solving the system like this, it doesn't know. Remember, we did this in the past when we had a system like that. So if we had a one-dimensional system, we did this. Now, this system doesn't know if the bigger system is one-dimensional or two-dimensional. It doesn't care. It's exactly the same way that you are going to solve the problem. Okay, it's very good. I wanted to actually come to this point. So we now know exactly how to assemble the stiffness of this system. Remember, this is basically what we wanted to do. We created node list, element list. We did the extended node list. We created the elements. We need to just assemble them, and actually you know how to assemble them. Shortly at the beginning of the next lecture, I show you the assembler stiffness, the assembled stiffness, and I just solve it to give you the answer. But this example is basically done, and all the examples that you have in your homework 2 and 3 and quiz 2 and 3, they will follow a similar process one way or another. All right. Thank you very much for your attention. Have a good day. Have a good weekend. Bye-bye.